Hello everyone, it is my great honor to have this opportunity to share my recent research. Today the topic is the numerical evaluation of and sensitivity analysis on dynamic heat transfer of a novel cadmium telluride-based vacuum PV glazing. My name is Changyu Qiu. I'm from the Hong Kong Polytechnic University. This presentation will consist of the following parts. Firstly, I will introduce the research background. As we all know that the BIPV system can be an alternative building element to replace conventional building materials. And it also can act as a power generation as well to produce the renewable energy. And the semi-transparent PV windows as a part of building envelope can admit a proportion of the daylight into the indoor environment. And from the previous research, we also can find that the semi-transparent PV window can perform a better daylight performance than the traditional windows such as the single glazing or double glazing. In terms of the thermal performance of the semi-transparent PV glazing, we can find that it has a very low solar heat gain coefficient. However, it is a lack of the thermal insulation ability. Therefore, it is not suitable for the heating dominant area. On the other hand, the vacuum PV glazing are considered as one of the best thermal insulation glazing technology. The thermal performance of the vacuum glazing is that it has a very low U value. The best vacuum glazing commercial product was reported with the U value of 0.68 watt per meter square per K. And next, this figure shows that once the window system can be classified into two categories. We can find that the PV glazing are considered as solar heat gain control window, and the vacuum glazing with the low E coating is one of the best low heat gain or heat loss window. And here is our ideas of the vacuum PV glazing. In this research, a novel cadmium telluride-based vacuum PV glazing is proposed to combine the advantages of the high thermal insulation performance of the vacuum glazing and the solar control ability of the semi-transparent PV windows. Firstly, allow me to introduce the structure of the novel cadmium telluride-based vacuum PV glazing. The proposed vacuum PV glazing consists of the vacuum glazing and the PV module in an integral glass unit which has only a 3-layer structure. The outside layer is the semi-transparent cadmium telluride photovoltaics with the transmittance of 40%. And the inside layer is the vacuum glazing with low E coating of the emissive of 0.06. As we can see that in this picture, we can see that clearly the semi-transparent effect, and in this picture we can see clearly that it has only 3-layer structure. And we developed a transient heat transfer model to investigate, to find out the dynamic heat transfer process of the vacuum PV glazing. And the boundary conditions the boundary conditions combines the we can see that the boundary conditions combines the conversion, radiation heat transfer and the convection heat transfer. And the developed heat transfer model was solved by the numerical solutions, which is the finite difference method. Based on the numerical solutions, the heat gain of the vacuum PV glazing can be found out for the given boundary conditions. And the dynamic heat transfer model was validated by a series by the experiment which is conducted in the solar simulation lab. The direct solar transmittance of the vacuum PV glazing is 12.5% on average. And we can find that the outside within a 1 hour solar radiation is exploded under the solar radiation of the 800 watt per meter square. The outside surface temperature dramatically increased from 13.5 Celsius degree to 66.8 Celsius degree. And the inside surface temperature, which is much stable, which only increased from 27.5 Celsius degree to 41.7 Celsius degree. And from these two figures, we can find out that in terms of the surface temperature and the heat gain, the simulation results are closely matched to the measurement data. Therefore, the validated transient heat transfer model can fully represent the dynamic heat transfer behavior of the vacuum PV glazing. Okay, so in this study, we analyzed the effect of the solar radiation on the heat transfer, solar heat gain coefficient based on the developed dynamic heat transfer model. We found that with the increase of the instant solar radiation from 100 watt per meter square to 900 watt per meter square, the dynamic heat transfer, the dynamic solar heat gain coefficient of the vacuum PV glazing increased from 0.146 to 0.148. And we also investigated the effect of the temperature on the U value for different scenarios. For the summer conditions, firstly, we can find that the heat gain dramatically increases when the solar radiation occurs. And the dynamic U value varies from 0.451 to 0.467 watt per meter square per K. And in winter, we found that the U value is lower than the U value under the summer conditions. In winter, the solar radiation could convert the net heat loss to net heat gain. And the dynamic, which means when there is no sun under the winter condition, it is the net heat gain, net heat loss of the vacuum PV glazing. But when the solar radiation occurs, there is a net heat gain of the window. And the dynamic U value increased from the 0.407 to 0.420 watt per meter square per K when the outdoor temperature increased. And we also investigate the environmental conditions, including the solar radiation, the ambient temperature, and the wind speed. The PV efficiency will decrease with the increase of the solar radiation and the ambient temperature, and will increase when the wind speed increase. However, the opposite trend can be observed on the effect of environmental conditions on the outside temperature, outside surface temperature. But we can find that the inside surface temperature is much more stable despite of the variation of the environmental conditions. And we conduct the sensitive analysis for the design parameters, including the PV efficiency, the PV coverage, and the low E coating emissivity. We can find that the emissivity of the low E coating is the most effective parameter on the heat transfer on the vacuum PV glazing, while the PV efficiency has little influence. And in terms of the sensitivity of the experimental conditions, we found that the dynamic heat transfer process is more sensible to the, firstly, we found that the dynamic heat transfer process is more sensible to the environmental conditions than the design parameters, especially the solar radiation plays a prominent part in the heat transfer of the cadmium telluride-based vacuum PV glazing. And the wind speed has a very little influence. In conclusion, the average dynamic heat transfer, the average dynamic solar heat gain coefficient of the vacuum PV glazing is 0.147 and will increase with the increment of the solar radiation. And the dynamic U value is higher under the summer conditions than the winter conditions. In both summer and winter, the most of the heat gain is due to the solar radiation, while the contribution of the temperature difference on amount of heat gain and or heat loss is much less. Thirdly, the solar radiation and the ambient temperature have a negative effect on the PV efficiency and a distinct positive effect on the outside surface temperature. However, the inside surface temperature is much more stable. The dynamic heat transfer model is more sensitive to the environmental conditions than the design parameters, especially the solar radiation play a prominent role in the heat transfer of the cadmium telluride-based vacuum PV glazing. For the design parameters, the emissivity of low E coating is the most effective parameters. That's all for my presentation. Thank you.